Okay, let's start. So this morning I'm your teacher and I'm going to talk about task space inverse dynamics, which I will shorten as psij. So get familiar with that, with those initials, you will hear them a lot. What is psij? It's a very popular control framework, especially in the legged robots community. And I will try to explain you why it is very popular, how it works, the theory and the implementation, and hopefully by the end of the day you will have it also installed on your machine and you will be able to play a bit with it using Python scripts. So everything started in '87 with a paper by Osama Khatib, which is very well known in our community, which is called the operational space formulation. And then this became a very active research topic, especially between 2004 and 2015. There have been plenty of papers discussing different ways of doing TSID. And I would say that now it's not a very active research subject. So it's a good subject for giving a class because it's stable, and tomorrow there is not a new paper that's coming out and it is revolutionizing how we do this kind of stuff. It's stable. That's how we do it, and I think it's not going to change much in the future. So the idea for today, at least for the morning, this is just the morning schedule, is we're going to start with some theory, 1 hour, 1 and a half. I have an idea, we'll see. Then in the second part, I will explain you the implementation details of the library TSID. There is a library that implemented this framework that I developed together with other colleagues when I was at class a couple of years ago. And then we will spend the last half an hour, 1 hour, depending on how much time is left, playing with the scripts so that you can get familiar with, get acquainted with how the framework works in practice. So before we start with the theory, let's talk a bit about setting up your computer to be ready for the last part, the coding part. You have 3 options. The recommended one is that you keep using the virtual machines that Nicolas gave to you yesterday. Hopefully most of you should have it working already. And you should just install in that virtual machine this TSID library. So the instructions for installing the library are posted in an issue on the GitHub page of TSID. So that's the address you should type in your browser. Open the latest issue. It's issue number 28. In this issue I posted a list of commands. It's, I don't know, 7, 8 commands that you can just copy paste in your terminal. A few people have already tried. It seems to be working. And if it doesn't work, then come and see me during the coffee break and we will try to fix it. If you don't want to use Nicolas' virtual machine, or maybe if you didn't manage to make it work yesterday, well, in theory you can just do the same stuff if you have everything installed in your native system. It doesn't need to be a virtual machine. Another option is to use my virtual machine that I prepared, and it's inside this USB key. So if you want, I can pass this around during the class so that people start copying it. It's a bit heavy, it's 11 gigabytes. It's much heavier than the one of Nicolas. It's because I prepared it with VMware Fusion and I don't have the Pro version of the software, so I cannot compress the virtual machine. The other option, if you're really hardcore, is that you install everything on your native system. And if you want to do that, just be aware that we are in this hybrid situation where we have 2 different versions of Pinocchio that are currently around. One that is shipped with the binaries and that correspond to the branch master of Pinocchio. It's a version 1. and that is compatible with the branch master of psij. Otherwise, if you're using the branch level of Pinocchio, that corresponds to Pinocchio version 2, and in this case, you should use the branch Pinocchio v2 of psij. Any question? Does anybody want my virtual machine?
Is the Pinocchio v2 branch the one we'll install in Nicolas?
Yeah. Yeah, in Nicolas VM, Nicolas installs Pinocchio v2. So if you use the instruction that you find on this issue, it will install the branch Pinocchio v2 of psij. The differences are minor in terms of functionality, nothing changes. It's just a matter of being compatible because they changed the namespaces. That's the main difference. Okay, shall we start with the theory? That's good. You're excited. I can see it. So, before delving into the theory, let's just define a bit of the notation that I will be using. It's very classic. The state is denoted by X. The control is denoted by U. Control theory notation. Identity matrix is denoted by I. Zero matrix is 0. Surprise, surprise. And sometimes I will be writing the size of the matrices as indexes, like identity matrix of size 3 is I with 3 as an index. Another thing I will be talking about a lot is fully actuated systems versus under-actuated systems. So let me get this clear right away. If the number of actuators of a system is equal to the number of its degrees of freedom, then the system is called fully actuated. That's the case for a classic industrial manipulator like the Cook arm. It has 6 degrees of freedom. Each degree of freedom has a motor associated to it. That's a fully actuated system. That is not the case for a legged robot, like a biped or a quadruped, because the number of degrees of freedom is more than the number of actuators. The reason, as Nicolas was explaining to you yesterday, is that for representing a legged robot, you have to introduce 6 extra degrees of freedom representing the position of its base, the so-called floating base or free flyer, that represents its displacement with respect to an inertial frame. And those extra degrees of freedom are not actuated unless you attach some propulsor to your robot and you make it fly. If you attach 6 propulsor to the floating base of your robot, of your legged robot, then it becomes fully actuated. But I've never seen such a thing. So classic legged robots are under-actuated systems. And that's important for what we are going to see. So that's it for the notation. That was the most boring part. The table of contents for the first part of the lesson is this one. We're going to first talk about actuation models, because depending on how you decide to model your actuators, well, then this is going to heavily affect how you shape your control system. Then we're going to talk about how we model tasks. So tasks are objectives. They are things that you would like your robot to do. And it's important that we define them in a proper way. And then, once we have a model for the actuation and a model for the task, we will see how we can use them together with optimization to write down a controller, an optimization-based controller that is going to try to achieve a certain task based on a certain actuation model. Then we're going to see how we can extend this in the case where we have more than one task. We have multitask control. And finally, we are going to discuss a bit computational aspects. So let's start talking about actuation. Everything starts with a model. Not really, but for today, it does. We will see on Thursday that you can use model-free reinforcement learning, and there you have no model. And it's really important to choose the proper model for your robots, because if you start with the wrong model, no matter what you do after that, nothing is going to work, right? So how do you choose the proper model? That's very difficult. It takes experience. And the proper model depends not only on the robot that you're trying to control, but also on the task that you would like the robot to perform. So for the same robot, you could end up using different actuation models depending on the task that you would like the robot to perform. We are not going to do that, but in theory that's possible. So we're going to discuss 3 different models for modeling the actuators. Velocity, acceleration, and torque. In the end, the only one we're going to use for the rest of the day is the torque model, but I think it's important that you are aware that also these other 2 models exist and they are appropriate in certain situations. So the simplest model you can use is to assume that your motors are generating velocities. So you can directly change instantaneously the velocity of your actuators, so the velocity of your degrees of freedom. That's a very good approximation for hydraulic actuations. It can also be a good approximation for electric motors, but only in certain situations. Like if you have an industrial manipulator that is not coming in contact with the environment, it's just moving in free space, it's quite reasonable to assume that you can control the velocity of the system. And that's how most industrial manipulators are controlled. They assume that they can control the velocity. It's not a good model for electrobots, so we are not going to use it. So in this case, the state of the system is just its configuration. So for a manipulator, it would be the angle of each joint. And the control inputs, of course, are the velocities. So the dynamic is just a simple integrator. So the velocity is equal to the control. You just integrate once. A bit more advanced model is to assume that your actuations are acceleration sources. So you can directly change instantaneously the acceleration of your degrees of freedom. This is a better approximation for electric motors, but only as long as you don't have large contact forces. So again, it's not a good idea for elect robots because the elect robot is always in contact with the ground for locomotion, and so you have large contact forces that are approximately equal to the weight of the whole robot. So in this case, the main difference with respect to the previous case is that the states does not include only the configuration, so the positions, but it includes also the velocities. The control inputs are the accelerations, and the dynamic is a simple double integrator. So the last and best model for actuators is to assume that they are torque sources. So they generate torques, or more in general forces, in case they are linear actuators. But for legged robots, typically they are angular actuators, so we typically will talk about joint torques, not joint forces. Yes?
Just a small question. When you say the best, you mean the best between these 3, or
the best
really
between these 3 and for the application that I have in mind.
Okay.
So the state is, again, position and velocities, as it was for acceleration, but this time the control inputs are not the accelerations, but they are the joint torques. So the dynamic is a bit more complicated than a double integrator, even if it is kind of similar in a certain sense. So let's take a look at the dynamic. Thankfully, Nicolas already explained to you the dynamics of a mechanical system yesterday, and hopefully he used the same notation that I am using. So you should be already familiar with this equation. you have M, the mass matrix, times U dot Q, that are the accelerations of the robot, plus H, which are the bias forces or nonlinear effects. This goes with many different names. Basically, this includes Coriolis, centrifugal effects, and gravity. Equal to tau, which are the joint torques, or more in general, they are the forces generated by your actuators, plus J, which is the Jacobian associated to the contact points, assuming your robot is in contact, otherwise you don't have the last term, times F, which are the contact forces. Okay, you should be already familiar with this equation, just tell me if you're not. Okay.
So either tau or F can contain forces and torques.
Yeah.
In general.
Yeah.
Okay.
Actually, they are the same. Just that tau are the forces, torques generated by the actuators, and F, they are the ones generated by the contact with the surrounding. But they can be both Newton or Newton meters. It's just that typically the actuators on a legged robot are angular, so we talk about torques. And F, we should talk about wrenches, to be more precise, because they can be both forces, so newtons, or moments, so Newton meters. So as I was saying before, the bias forces, so H, can be decomposed into two different terms, but we don't care about that for today, just for your information. So the dynamics that I just described was the one for a fully actuated system. So number of actuators equal number of degrees of freedom. What happens if your robot is under-actuated, which is the case we are interested in, because that's the case for legless robots? Well, in this case, we're going to introduce some new notation. Let's call NVA the number of actuators, and NV the number of degrees of freedom. So we know that for an under-actuated system, NVA is less than NV, because we have less actuators than degrees of freedom. In this case, we can order the elements of the configuration vector so that we have first all the elements corresponding to the unactuated degrees of freedom, and then we have all the elements corresponding to the actuated degrees of freedom. We will call them QU. U stands for unactuated, and QA, which stands for actuated. Same for the velocities. And we can introduce this S matrix, which is a very simple matrix. You just have zeros on the left and the identity matrix on the right. It's a selection matrix because if you multiply S times the velocity vector, it selects only the velocity of the actuated joint. Okay. Why do I introduce this matrix? It's because I need to use it in the dynamic equation of an under-actuated system. So you can see that the dynamic hasn't changed much. The only thing that has changed is that now here we have this S transpose matrix, which basically means this vector here is not as big as this vector here. This is smaller. And so we need to add zeros on top, which correspond to the unactuated degrees of freedom. So for the unactuated degrees of freedom, the force generated by the actuators is zero because there are no actuators generating force on the unactuated degrees of freedom. That's quite simple. So we just introduce this matrix S transpose in the dynamics. It's a very little change, but it affects a lot the behavior of the system and your capability of controlling the system. And very often you will see that people split this equation into two different parts. Since we have above all the unactuated degrees of freedom and below all the actuated degrees of freedom, you can split the equation in two parts. You have the unactuated dynamics and the actuated dynamics. And here you can clearly see the effect of the S matrix, because the joint torques, so your actuation forces, only appear in the equation below, but they do not appear here. In the unactuated dynamic, you don't have your actuator forces, you only have the contact forces, which already suggests that in order to control your system completely, you need to pay special attention to your contact forces, because it's only the contact forces that affect the dynamic of your underactuated part. That's just notation, but it will be useful because we will use this notation later. So you need to be familiar with that. Okay. Am I going too fast? Are you keeping up? Okay. So let's talk about task models. Hopefully, if you want to control a robot, you have a task that you would like the robot to perform. You're not just playing around. So the question is, how do you model your task? So we will use the task function approach, which is a very old approach, which shares the same spirit of optimal control. That is, we describe the task to be performed as a function that we would like to minimize. And in practice, we will see that the function that we would like to minimize has its minimum at 0. So it's a function that we would like to drive to 0. And this function, without loss of generality, we will assume that represents an error. It's an error between the value of a certain output function and a certain reference function. So we would like this output to follow this desired reference. The reference can be time varying, so it depends on time. And the function, the output function, can depend both on the state and on the control of the system U. So I said before that this is similar to optimal control, but actually it's not exactly the same if you pay attention. Because in optimal control, the function that you want to minimize is a function of the trajectory of the system. So it's actually a functional. Instead here, we are just working with function of the current state and the current control of the system. So it's instantaneous. It's not an integral through time as it is in optimal control. So it's similar, but not exactly the same. So in practice, we will encounter 3 kinds of task functions. You can have task functions that depend on the control inputs, U. They can depend on the robot velocities, V, Q. Or they can depend on the robot configuration, Q. And for some, yeah.
So are those left-hand terms, like the Y of V, Q, are they also functions of time? So we have the same time variable in mind.
They are function of time, but here you see them as just the current value.
Okay.
So you don't look at their future evolution.
So we're saying yes, but we pick them to be at the same time t, that's the reference, which is a function of time.
Yeah, sure.
Yeah.
Sure. So for some reasons that we will see shortly, we can handle nonlinear functions of the robot's velocities and configuration, so of the robot state, but we will have to stick with only affine functions of the control inputs. I will come back to this point later to make it clear. So the issue here is that what we can instantaneously control and select are the control inputs U. We cannot choose the state of the system. The state is given. Only the derivative of the state is affected by the control input. But we cannot change instantaneously the position of a body in space. We can change maybe its velocity, or in this case, its acceleration, because we are assuming that our actuators are torque sources. So we can only affect the second derivative of the configuration of the system. So we can directly satisfy affine functions of the control inputs, but we cannot directly impose a function of the velocity or the configuration. So the trick to try and minimize function of the velocity and the configuration is to impose a dynamic of this function. So we're going to affect the derivatives of this function in such a way that the limit for time going to infinity of this function tend to 0, because that's the minimum we would like to achieve. So let's see how it looks in practice. Let's start with the case of a function of the velocity of the system. We have this error function e, which is nothing more than the difference between the output function y and the reference y star. Since we cannot change the error function instantaneously, we can only change its derivative. What we can do is that we can impose a first order linear dynamics for this error function. It's as simple as that, e dot equal minus ke. And if you're a bit familiar with linear dynamical system, you can recognize that if k is positive, this is a stable dynamical system. Yes? Okay.
I was just mimicking the...
Okay. It's a stable dynamical system, which means that E will tend to 0 for time going to infinity. It will actually never reach 0, but it will tend to 0 fast enough. And after a while, you don't care if it's not exactly 0, but it's 10 to the minus 9. So, okay, we can impose this linear dynamics, but how does it look in terms of the joint accelerations? Well, we can express E dot as y dot minus y dot star, because that's the definition of E. And we can express y dot, since y is a function of the robot velocities, we can express it as a linear function of the robot acceleration, using the chain rule. And this guy here, so the gradient of y with respect to the velocities is a Jacobian. It's the same Jacobian that Nikolai explained to you yesterday. And it's the same Jacobian that it's appearing inside the dynamics of the mechanical system. So in the end, we have this affine function of the accelerations of the robots. So the Jacobian time acceleration, we would like it to be equal to this. And we will see later that the fact that we get an affine function, it's very important for computational aspects. And we can, well, in theory, and this is something that I only realized when I was preparing the slides, in theory we are not forced to impose a linear dynamic here. We could also impose any nonlinear dynamic, as long as it forces our system to converge to 0. But in practice, almost nobody uses a nonlinear dynamic. We could, but we don't. In practice, it's not necessary, and a linear dynamic works very well. Well, maybe some people add some saturation, so it becomes slightly nonlinear, but it's mostly linear.
What was y again?
Y is an output. It's an output function.
Okay.
So, in practice, some example, y can be the position of an end effector of the robot, or it can be the position of the center of mass of the robot, or it can be the joint angles of the robot. It can be anything that you would like to control. It's a general function of the robot state or control inputs, that the user can define and say, okay, this is a function that I would like to control, and I would like this function to follow as closely as possible this time-varying reference.
I think I'm missing the point here. So how is the last equation there similar to the initial one? There is the derivative of the first equation, no?
So
I'm missing.
this is the linear dynamics that we want to impose.
No, I see the development,
Okay.
but then you get to a point where that's not the error function on top. So when
No.
you say this is affine with respect to what, I don't see.
So
The
we
point
saw in the previous slide that we cannot instantaneously change the error function when it depends on the state, because instantaneously we can only change the control inputs. So we can only instantaneously change this kind of function, whereas for this and this we cannot change them instantaneously. So the only thing we can do is that we can impose their derivative, first or second, such that this error function tends to zero as time goes to infinity. So this is exactly what we did here. We have this error function, and we say, okay, I would like this error function to follow this linear dynamics. And then I express that as an affine function of the accelerations of my robot. And we will see why that is good. The intuition is that we can only control the control inputs, which are the joint torques, and the joint torques are affine to the acceleration. So we can kind of control the accelerations, or at least try to.
Okay.
So if you have a linear function of the accelerations, well, that we can impose.
So you say it's affine because it's actually linear, no?
It's affine because if you represent it as a function like f of v dot equals 0, you have the linear term and the constant term. So affine, in my vocabulary, maybe I should have defined that. Affine means linear plus constant. That's from Stephen Boyd. I took his vocabulary. Maybe that was not trivial.
Okay.
But yeah, I may also be using linear and affine to describe affine and linear. Sometimes I switch them. I use them a bit loosely.
Okay.
So the difference between, you say this is different from optimal control in the sense this does not require transcription or discretization. Is
Yeah.
that the difference?
Yeah. Because we are working only looking at the current state of the system. We are not looking at the future evolution of the system as optimal control does. Okay, this may be a little bit hard to digest, but hopefully it will all come together when we get to the formulation of the control problem, which is in a few slides. So bear with me. So for task function that depends on the configuration of the system, we can do something that is very similar to what we just saw for the case of velocity-dependent function. Just that the only difference is that in this case, we cannot impose the first derivative of the system, but we have to go to the second derivative because we want to reach the acceleration level, because it's only at acceleration level that our control inputs are acting, because we have a second order system. So second order linear dynamics, again, we could go for nonlinear dynamics, but nobody does that. We all are happy with our linear dynamic. And again, we can express E double dot as an affine function of the robot acceleration. So here we have the developments, we don't care, it's simple. We get an affine function, and as I said, in theory we could have imposed nonlinear dynamic. So let's summarize what we have seen in this part about task models. we have seen that we can define task functions that we want to minimize to describe the objective of the controller and the robot. And this function can depend either on the state, x, which contains position and velocities, or on the control, u. Function that depends on the control must be affine. We will see why in a few slides. Instead, functions that depends on the state can be nonlinear. Only requirement is that they are smooth, because we derive them, so they need to be smooth. For functions that depends on the velocity, we can impose the first derivative. Function that depends on the state, on the configuration, so position, we can impose the second derivative. And regardless of which kind of function we have, through the methodology that I just described, in the end, what we get is an affine function of the accelerations of the system, v dot q, and the control inputs. And from now on, we will just describe it using this notation. So a, y, I just realized that here y is not the same y that I've been using in the previous slide, sorry. My mistake. But okay, from now on, y will represent this variable and will no longer be the output function that I just described to JJ. And we will call this affine function g of y. It's a lot of notation maybe to digest, but I will try to remind you of what each symbol means as we go through. Okay, so we have seen how to model the actuators of our system. We decided to stick with the assumption that our actuators are generating forces or torques. And then we saw how to model the task we would like our robot to perform by using this task function approach. And in the end, we get these affine functions of the robot accelerations and control inputs. Now we can see we will see how all of these come together in an optimization-based context to define our controller as an optimization problem. So the key idea is that we can formulate control problem as optimization problems. It's not a new idea, it's how optimal control works, basically. But here it's done in a slightly different way. So the key elements of this optimization problem are going to be the state of the system. You're already familiar with that. The control inputs, U, which are actually equal to the joint torques in our case. The dynamic of the system, we will start assuming the system is not in contact, so we don't have the J transpose F term in the end. And we have a task function to minimize. So the functions that we have been working with so far were vector-valued functions. So G actually is a vector, it's not a scalar. So you cannot minimize a vector, it doesn't mean anything. You can only minimize a scalar. So what people typically do is that they minimize the 2 squared norm of G. I think also Nicolad talked a bit about minimizing quadratic function. Well, this is going to be a quadratic function because it's a square of a linear function.
So here you're talking about, not talking about a humanoid, right? Not talking about, because it's not
yeah,
contact forces.
This is only an under-actuated system, but without contact forces. We will add the contact forces in a few slides. Doesn't change much. Okay, so this is TSIG. This is task space inverse dynamics. It's this optimization problem. So the variables of the problem are y, which contains the accelerations, v dot, and the joint torques. And this is all we need to describe the dynamic of the system. So the dynamic of the system is a constraint, equality constraint to be precise, and the cost function is a quadratic function of my variables, which are acceleration and torques. So since we have affine equality constraints and a convex quadratic cost function, this problem is a convex quadratic program, QP in short. But to be more precise, the cost function is not a general quadratic function, it's the square of an affine function. So it's a very special kind of convex quadratic. To be precise, the reason is that if you develop this, you write it down by multiplying this times itself. You can see that the linear term, which is A transpose, capital A transpose A, is always in the rate space of the Hessian, because you have A transpose in both. And this can be exploited somehow in the resolution of the optimization problem. So this is actually not a generic quadratic program. To be more precise, it's a least squares problem. We don't care much. From now on, I will be talking always about quadratic programs, QP, but sometimes I may also refer to it as a least square program. So you know what these two means and what's the difference between them is. So, as Ahmad pointed out, that did not describe a lect robots because we took the assumption that there was no contact between the robot and the environment. Well, it could be a lect robot in space, just floating, or it could be a lect robot jumping, but when your lect robot has its feet on the ground, then you have contact forces. So, how do we modify that problem for the case where we have contact forces? Well, we just add the contact forces to the dynamics, right? But it's very different if the contacts with the environment are soft or rigid. So if they are soft, meaning there is some reasonable compliance at the contact interface, then what you can simply do is that you can measure the contact forces and you can inject them in the dynamic. So the only difference between the case where you have no contact is this. Well, it doesn't work. You just need to add this term to the dynamic where F hat is the measurement or the estimation of the contact forces. But it's a very small difference with respect to the problem we had before. We will see that instead, in the case where the contacts are rigid, which is the case we are really interested in, because typically the interaction between the feet of the robot and the ground is modeled as rigid. Of course, it's not perfectly rigid, but that's a reasonable approximation. In the case where the contacts are rigid, they are constraining the motion, meaning that once my foot is in contact, well, once my hand is in contact with the wall, I can no longer move my hand in that direction, right? And that is a constraint. It's something that I cannot do no matter how I push. I can push as much as I can, but I cannot move in that direction. So this is a constraint. And this changes how we model things. So we can model constraints similarly to how we model tasks. So we use just a nonlinear function. In this case, I simplify things. It's a nonlinear function of the configuration of the robot, because that's the case we are interested in practice. And this linear function basically just says that the points of the robot that are in rigid contact with the environment, well, they don't move. And here there is a big assumption behind this model. the assumption is that if I'm in contact, I do not break the contact. Because of course, the contact points can move typically because you have unilateral contact. You can move, but only in one direction, and by breaking the contact. You cannot move in the other direction. So the assumption that is always taken in psij is that if I introduce a rigid contact, I'm implicitly assuming that the robot won't break this contact. So I need to know in advance if the robot is going to break the contact. And in this case, I do not model the contact, because if the robot is going to break it, then it doesn't matter if there is a wall on the other side, because I'm moving on the opposite side.
So you're not considering sliding on the contact, like
No.
slipping. Okay.
Maybe that's possible, but I haven't seen people doing that. I should think about it. But no, basically once you're in contact, you stay in contact, and once you want to break the contact, basically you just don't model the contact anymore in psij. You remove the contact.
Could we model it with inequality constraint?
Yeah, I'm getting to that.
So you basically assume that I will be the one handling the
Yeah, so the user
Okay.
needs to decide for the control framework when it is time to break the contact. So yeah, psij, you should think of it as a controlled framework. It's not something very smart. It's not doing planning. It's not even doing optimal control, trajectory optimization. It's something much more simple and basic. It only looks at the instantaneous state of the system, and given some specifications that are given by the user, it decides what are the actuator commands to send to the motors. It's not very smart. We will see that.
So the C function can take on value of 0 and positive real numbers?
So the C function is how you define your constraint, and actually what's inside that C function, it's simply the position of my contact point on the robot is equal to the position of the contact point in the environment. So the two things should stick together. They cannot separate.
If it's non-zero, it's...
If it's non-zero, it means you're violating the constraint, which means either that you broke the contact, but without wanting to.
The range of the function is not a binary variable. It's a
No, it's not that binary.
Okay.
No, it's a continuous, smooth variable function. In practice, it's actually very similar to the task function describing the position of your end effector or the position of your foot. It's just in this case, it represents a constraint, not a task or an output. But in practice, what it is, it's a forward kinematic function that probably Nicola talked about yesterday.
So just to be sure, when you say a constraint, it goes below the arc mean. It's like it's subject to this.
Exactly.
And-
Exactly. And we will see how we're gonna put it there. Actually, the way we are going to include this inside the QP, the quadratic program, is exactly the same way that using the same tricks that we used for the task function. So this is a function of the robot configuration. We cannot affect the configuration instantaneously. We can only affect the accelerations. So what we need to do is to take derivatives. So we derive it once, and we get this. And this, what does it mean? It means the velocities of the contact points are null. And then we derive it a second time, and we get this. Maybe you're familiar with that. It would be really helpful if you're familiar with that. And this, in words, it means the contact point accelerations are null. And since at the moment where you start having the constraint is satisfied at that instant in time, just by imposing that its second derivative is null. You're also imposing that its first derivative is null, and that the function itself is null. Okay, you have a function that is 0, and its derivative is 0. You impose that the second derivative is 0, well, also the first derivative is going to remain constant, that is 0, and the function itself is going to remain constant, which means at 0. So by imposing the second derivative, we are implicitly imposing also the function constraint. Yes, Michele?
The position should be constant, not 0. You have a location, a specific location.
That's already inside C.
Okay.
So C is the difference between the location of the contact points on your robot and the location of the contact points in the environment.
Okay.
Yeah.
You say that by imposing the second one, you satisfy the first?
Yeah.
What about the constant velocity? If you impose the second one, the last term, or you impose the two last equations?
Well, I didn't write it down, but the assumption is that when you are in contact, you have zero velocity.
Yeah, of course, but you cannot ensure this by just imposing the acceleration equation. I mean, one.
So if C is equal 0 and C dot is equal 0.
Yeah. Then you get the last
Then
equation.
by imposing the C double dot is equal 0, C dot will stay 0 and C will stay 0, right?
I think it's saying if you just impose the third equation, it doesn't imply the second equation.
I mean,
No.
the first implies the second, implies the third, but not in reverse.
Yeah.
Yeah, but it's in the state, right?
Yeah, but so there is some context. In general, you're right. I agree. You can only work down, but you cannot work it up. But here we are talking about rigid contacts. So the idea is that you activate the contact constraint when you're in contact. And if I'm in contact, it means that the first is satisfied and the second is satisfied at the moment where I am in contact.
Yeah. So that makes initial conditions.
Exactly.
Yeah.
I have the initial conditions, and then I will only impose this. And given the initial conditions, this implies this, which implies this.
Okay.
So you should be careful. The moment you activate the contact point should not be sliding. Otherwise, you're going to violate the contact constraint, as you pointed out.
Right. Okay.
Yes?
In practice, in the solver, don't you need to put some kind of feedback so that you, let's say you encode at the second order level, so the jv.q.
So, okay.
Put some kind of KPE, KDE dot.
That's kind of advanced questions that I kept for later.
Okay.
But to answer you, you should differentiate simulation and reality. So in reality, you don't because even if you have a small drift, you have the friction forces that are going to prevent you from sliding and drifting. In simulation, I typically thought that you should do that, and we will do that in the scripts that I will give to you later. But actually, yesterday I made a test. I removed the feedback term, and I integrated for 1 minute, and it didn't drift. So I thought it would drift, and it would have made a nice example to explain why people typically do that, but I couldn't make it drift.
But so maybe it depends on the cases where, so imagine you start where you're in a case where you're not moving a lot, and in that case maybe it doesn't drift, but I guess maybe through making some kind of walking motions, so your foot lands, and it's supposed to follow kind of reference trajectory, but it doesn't follow it precisely, and then you end up with some kind of residual velocity, and then you drift.
Yeah, in practice, I've always put some feedback,
Yeah.
but in the examples that I will give to you,
Yeah, you
it
don't-
works even without feedback. But it's only for simulation, actually. I mean, it's only a problem in simulation. In reality, it doesn't matter much. Okay. So we have the contact constraint saying that the contact points will move. We derive it twice to express it as an affine function of the robot accelerations, which are part of the variables of our optimization problem. And this is the new psij problem, assuming a robot that is in rigid contact with the environment. So we see here that the problem has changed quite a lot with respect to the case of soft contacts, where we only added the estimated contact forces. Because here we have not only the dynamic of the system, which is represented by this equation here, but we have also the contact constraint, which are these ones. The cost function is the same, it's a least square function. So the main difference is that we have this new contact constraints that are saying the acceleration of my contact points is null, and so this implies that my contact points don't move. And this is the problem that we are going to work with in practice later when we will be coding.
One thing, J is the same in all the appearances of
Yeah.
J are
Yeah,
the same
exactly.
J.
Good point. So this J here, that is the Jacobian of the constraint, is the same J that maps the contact forces in joint space.
And so how, because you have 3 columns on the first matrix? Ah, okay, they map V dot, F
Yeah,
and tau.
we
Okay.
added, yeah,
Okay, okay.
I forgot to mention, we added the contact forces as an optimization variable. So if I remember correctly, Nicolas was mentioning something about having the contact forces as optimization variables inside your problem. Am I right, Nicolas?
Yes, but you can re-explain it, I think.
Okay.
But then is it just dimension-wise, then V, Q, and F have the same dimension? Because both are mapped by big J.
No.
If you look at the
So
equation.
J multiplies V dot,
Yeah.
and J transpose multiplies F.
Ah, transpose. Yeah.
Yeah,
Okay.
there is a transpose there.
Good. Yeah, that's
And tau instead is not multiplied by J.
okay.
Didn't you say that the F is measured? The
So
contact
F
force
was
is
measured before when we were assuming soft contacts.
Mhm.
So a soft contact would be something like this. This is a soft contact. And in this case, there is no constraint because my hand can move. It's just that the more I move into the contact, the higher the reaction force I get. But I'm not constrained.
Okay.
Instead, if I'm in contact with a rigid surface, then it's different.
So,
I cannot move in that direction.
so in the case of rigid contact, the contact force is the one that you can determine in the.
So in this case, I don't need to measure the contact forces. That's a big difference. Actually, that's one of the advantages behind the choice of rigid contact rather than soft contact. In the case of soft contact, I need to estimate or measure the contact forces. In this case, with rigid contact, I don't need to do that. And actually, you can show that in the case of rigid contact, the contact forces are a direct function of your control inputs, of your joint torques. So by selecting your joint torques, you're indirectly selecting also your contact forces, which is why we can model the contact forces as a variable of our optimization problem. Basically, the solver is selecting the contact forces that we would like to see. Yes?
Once you play this torque trajectory on the robot, do you like track the contact force as well? Like try to ensure you get the same forces you simulated, or?
No, that's a good point. The classic way, the standard way, let's say, to use psij on a robot is to have a torque-controlled robot, where you can control the torque at the joints, and you only care about tracking the torque. You don't care about measuring or tracking the contact forces, because in theory, if everything follows the modeling assumptions that you took, the contact forces are directly implied by your joint torques. So you don't need to measure the contact forces. And actually, that's also kind of a problem of these assumptions, because if you have a force sensor at the contact location, so you have a direct measurement of the contact forces, there is no way to use that, to exploit that inside this control framework. So actually that's an active research topic. How to exploit contact force measurement inside this kind of optimization-based control framework. Okay. So let's discuss a bit debate quadratic programs versus using pseudo-inverses. So if I remember correctly, Sylvain yesterday talked a bit about pseudo-inverses for solving least square problems, right? Okay. So far we have only seen least square problems, so LSP, with equality constraints, right? That's the only thing that I've showed. And as Sylvain pointed out yesterday, if you have an unconstrained least square problem, which is a problem that looks like that, you can solve it directly using just a pseudo-inverse. So this symbol there represents the pseudo-inverse of the matrix A. So you don't need to download a QP solver. You can just use a NumPy or Eigen, whatever library you're using for linear algebra. You compute the pseudo-inverse of the matrix, you multiply it times the vector A, and you get the solution of this optimization problem. It's the simplest optimization problem you can solve because of this. And actually, even in the case where you have equality constraints, so you want to solve this problem here, minimize a least square function subject to a linear equality constraint. Even in this case, you can solve it just using pseudo-inverses, and this is the solution. Where this matrix here, and B is the null space projector of the matrix B, which is defined in this way. Details, that's not the point. My point is, if we can solve this kind of optimization problems using pseudo-inverses, why should we bother using a QP solver? And actually, since, before 2010, very few people were using QP solvers. Everybody was using pseudo-inverses to solve TSID. It's only been recently, in the last 8 years more or less, that people have started to use QP solver. And the reason for that is that QP solvers can also handle inequality constraints. We haven't seen that so far, but I'm going to use it in practice. And inequality constraints are extremely useful because they allow you to represent the bounds that are acting on your system. So for instance, you can represent the joint torque bounds. So your motors are going to have a maximum torque that they can generate and a minimum torque. You can include that inside the optimization problem. The contact forces, which are a variable of the TSID problem, typically are constrained to stay inside friction cones. So you can represent that by linearizing the friction cone, which is quadratic typically. You linearize it and you represent it as linear inequality constraints. Or you can, your robot has also bounds in the joint positions, right? I cannot go beyond this point. And in the joint velocities because of the motors. And you can translate this joint position and velocity bounds into joint acceleration bounds and include them inside the psij problem. So in the end you get a least square program with both equality constraints, which are the dynamic of the system, and inequality constraints, which represent the bounds that you have on the physical bounds you have on the system. And all of these are taken into account when choosing the control inputs, the joint torques. Yes, Steve?
No, okay, I just had my ink shop, sorry.
Okay. So I can see you're tired, and I can understand why. We have still 20 minutes to go before the break. Do you want a micro break of 3 minutes? Or shall we move forward? Okay, nobody said yes, so we move forward. So far we have only been discussing about single task control problem. So you have one task that you would like your robot to perform, and you want to find the motor commands to make this happen. But what if you have a redundant robot with many degrees of freedom that has to perform a very simple task? Like you have a 7 degrees of freedom manipulator, and you want to control the placement of the end effector, while you have an extra degrees of freedom, right? I can keep my end effector in the same placement, but I can still move my arm because I have 1 degree of freedom more than the dimension of the task I want to perform. And this is even more pronounced in the case of our legged robots, because typically these are highly redundant systems with many degrees of freedom. And the main thing you care about is balancing, which is well encoded by the center of mass position. So you may have 30 degrees of freedom for your legged robot, but you want to control the center of mass, which is 3 degrees of freedom. So what do you do with the extra degrees of freedom that you have? Well, it's actually cool to have extra degrees of freedom, because so you can account for secondary tasks that you would like your robot to perform. So in the case of the manipulator, maybe you want to keep the elbow as high as possible, because here there is an obstacle and you don't want your robot to risk hitting the obstacle. Or in the case of the humanoids, sure, you want to control the center of mass, and if you're walking, you want also to control the placement of the feet, but maybe at the same time you would like the robot to look at your arm. And that's not as important as keeping the balance, but if possible, why not do a secondary task? Or maybe you like the robot to do something with the hands while it's walking. You can use your imagination. So the question is, how do we incorporate these secondary tasks inside the optimization problems that we have just seen? And there are different ways of doing that. The simplest approach, and that's the one we are going to be using later during the lab session, is to use weights, which are also called soft priorities. So you have your capital N tasks. Each task is defined by a least square cost function, as we have seen before. And what you're going to do is that you're simply going to sum all of these cost functions using weights, W. And where do these weights come from? Well, it's up to you. You have to decide the weights. So the higher the weight, the more important this task is for you. So you have to tune the weights. They are very similar to doing gain tuning when you have to tune your PD controller. You have to tune the weight so that the behavior of the system is satisfying for you. So they are user-defined criteria. And the pros of this approach is that actually the optimization problem hasn't changed much. So instead of having a single least square function, you have the sum of least square functions, which is a least square function. So it's the same problem. Mathematically speaking, it's exactly the same problem we had before. Nothing has changed. So in terms of computational efficiency, it's the same. The concept of this approach is that finding the right ways can be hard. It may require some experience to do that. And also, if you start having many tasks that you would like the robot to perform, and the level of importance of this task relative to each other is very different. You have some task that is really, really important, then another that is medium important, another a bit less important, and yet another that is even less important. Then you want these weights to be very distant from each other. And this can lead to numerical issues because you may end up with a cost function that is ill-conditioned. It's a bit technical, but just keep in mind weights can lead to numerical issues. Yes, Michele?
But also the scaling issue, I mean, the variables are trying to control can have different magnitudes, so it's not just a matter of importance of the weights in microns at least.
Yeah. When tuning the weights, you should keep in mind the scaling of the variables that you are summing together. Yeah, you're right.
So how easy is to get a GI which has some metric, like it's usually...
You don't.
You don't?
No. No, in terms of unit of measurements, there you're summing pairs and apples.
Yeah.
And you have to live with that.
Yeah, okay.
I mean, you can try to a bit compensate for that by selecting W properly.
Yeah, but before selecting W's, it's just to help selecting W's. But yeah, I know. Yeah. No way.
I don't know of any proper way of doing that. Let's put it this way.
Of selecting W.
Of selecting W and taking into account that you have different unit of measurements inside G.
And this allows for degrees of freedom to overlap between the tasks.
Yeah.
And could you not get a stage where as you come very near to completing an important task, the smaller weighting on a less important task nonetheless makes that the larger contribution to the cost function? And so you never fully complete any...
Yeah, you have this problem. So those are called soft priorities because they are soft, meaning that there is not one task that is infinitely more important than another. Okay, you're always looking for a trade-off in theory. In practice, you don't care. Because if a weight is 1,000 times bigger than another, the effect that you have is as if you had a strict hierarchy, strict priority between these two tasks. It only becomes important if you have many tasks, as I was saying before. Assume you have 4 tasks, and you want to keep a ratio of 1,000 between each task. You get to a ratio of 10 to the power of 12 between the most important and the least important task. And 10 to the power of 12 inside your Hessian matrix can lead to numerical issues.
Yeah.
So when you solve it, you actually just consider W fixed solving a like KP. You don't really do...
You could also change it over time.
So you do some continuation.
Yeah, you could change it over time. There are people who have been looking into learning the weight from demonstrations.
Okay, I see. Yeah.
Also for switching tasks, no?
For switching tasks, weights are quite useful because they allow you to
change one to the other one.
change. Yeah, before removing a task, you can just lower its weight, and when it's low enough, you remove it. And when you're introducing a new task, you introduce it with a very small weight, and then increase the weight until you reach the desired value. People do that. Okay. So the second approach is the one that our friend was suggesting, that is having strict priorities. So this is called hierarchical optimization. Yeah, strict priorities, prioritized, control, it has many nicknames, but they all mean the same. The idea is that instead of having a weight, you have just an order between the tasks. So you say, I have task 1, which is infinitely more important than task 2, which is infinitely more important than task 3, and so on. So in this case, you cannot solve just one single quadratic program, but you have to solve a sequence of quadratic program, one for each task. So what you do is that you minimize, when you're at stage I, you minimize the cost function I, and you add the constraint that the cost function of all the tasks that came before, so that are more important, should stay the same, should remain at its optimum. And it turns out that you can write this constraint here as a linear constraint. So the problem remains a QP, or a least square problem to be precise. So the pros of this approach is that it's much easier to find priorities than to find weights, because here you have a finite number of options, whereas with weights you have infinitely many options. But the cons is that you're not solving a single QP, you're solving a sequence or a cascade of QP, so it takes more time. Or you can also try to use a hierarchical solver, but there are no off-the-shelf hierarchical solvers available. The only one I can think of is the one that Nicolas wrote, but it's a research prototype, so it's not something super reliable that you can just use off the shelf. Correct me if I'm wrong.
Yeah, please don't use it.
You mean the hierarchical off-the-shelf solver?
Yeah.
But, I think, are there solvers for like say Pareto, like the Pareto front optimization? I think there. If you consider W as. Like,
yeah, but this is like, if you look at the Pareto front, here you're interested in the limit of the Pareto front in one of the two directions. You only care about that. You don't care about finding the whole front. So it's a very specific case. And the fact of being more computationally expensive, it's a big disadvantage since we are talking about real-time control, which is typically done very fast. We're going to see that in the next and final section.
Would it be possible to, for example, use the null space of the first task to control the second task?
Yeah, that's basically what you're doing by specifying this constraint here. This is just a high-level way of writing down what you just described. This means for minimizing this cost function, you can only use the null space of the previous higher priority cost functions. So in practice, what you do is that you use the null space of the previous task.
But if you use like the Jacobian operator, something like null space operator, I don't know exactly how you do that, but
yeah, you can use the Jacobian, the null space of the Jacobian.
Then can't you solve the problem in one QP instead? If you use that explicitly instead of solving several QP.
No, you have to solve several QPs. There is one special case in which you can solve a two-priority problem with only one QP, but that's a very special case. It's when one of your two tasks is a joint posterior task, so the Jacobian matrix is actually the identity matrix. In that case, there is a trick to use, but apart from that very special case, in general, you need to solve one QP for each task. Yes.
How is the case handled when the problem is under-actuated and there are several solutions to one optimization problem? Maybe you solve the first problem and you find 5 solutions, but only one of them is going to be compatible with later problems. This is not taken into account in the higher.
So, I see the first part of your question, that when you have a task that is, it has a dimension that is lower than the number of degrees of freedom, you have infinitely many solutions. That is what we call a redundant system. And so you have the extra degrees of freedom that you can use for the later problems. But I didn't get the question.
Okay. If my first task is to put my hand here, and the second task is to put my hand here,
okay,
and this is more important,
yeah.
Maybe I'm going to... Oh, is it possible that this solution will put me here, but in a position that I cannot reach this point? Or is it going to...
No,
okay.
it's gonna figure it out.
Okay.
Because when you're solving the second problem, you're gonna find a solution that minimizes the second cost function,
yes,
while satisfying the first one.
Maybe,
but you're not looking at the solution that you found before. You're only looking at the value of the cost function that you found before.
okay.
You see, there is no yj star here. So you don't care exactly about the control input that you found in the previous problem. You only care about the value of the cost function, which is gj star that you found in the previous problem.
I suppose maybe an extension though is, what if there's a set of movements that you had to do to perform task 2 that briefly violates the, say, end position of task 1? Even though as a kind of aggregate problem, both could be satisfied. So for instance, maybe if your space was very confined, and so there's no manipulation you can do to sort of put your elbow here while your end effector is here. But if you can move your end effector and do that, you can then get your elbow there, for instance. So
okay, I'm not sure. I kind of understand what you mean, and what you should keep in mind is that psij is quite stupid. So it cannot reason about the future evolution of the state of the system. It only looks at the instantaneous accelerations, basically. It's a framework that reasons only about accelerations. So you have a desired acceleration for task 1, a desired acceleration for task 2, and if you have a strict priority, so task 1 is infinitely more important, it will try to, first of all, get as close as possible to this desired acceleration, and then it will work in the null space of this to get as close as possible to this one. And if it's not possible, well, it's not going to do it. And you may actually end up in situations where, since you're only reasoning at acceleration level, a secondary task is having an effect over time on the primary task. That could happen. So actually, coming back to your question, it could happen not instantaneously, but if you're looking at the effects over time, over the whole trajectory, since psij is not reasoning about the whole trajectory, but only looking at the instantaneous acceleration, you can have this kind of negative effect. Okay.
And yeah, I'm not an expert in these solvers, but I assume that when you're solving for the second task, you're giving as an initial condition, as an initial value, what you found on task 1.
For the cost function.
But so what is the accessible, the valid space of the equality constraints is not connected? Is it still going to be able to find this other case, or does it need the continuous path between the two valid spaces? I'm not sure that's very clear.
What do you mean by value space?
Well, if to get from the first solution you find to the solution that solves both problems, you have to go continuously from one to the other. You need to go...
There is no continuation.
What if the second task has no solution, would the QP here be stop, or would try to find a solution for the third? Because maybe the third has a solution that satisfies the first, but the second can't.
So the second task has no
Say,
solution. Do you mean the problem is infeasible?
Yes. So
It cannot be.
It cannot be.
No. The only problem that can be infeasible is the first one.
Okay.
Because you may have constraints that are impossible to satisfy. But once you solve the first one, all the others by definition are feasible.
Okay.
Because you're just saying infeasibility can only be implied by the constraints.
Okay. I see.
And the constraints are satisfied by the solutions that you found in the first problem.
Yeah.
So by definition, a solution exists.
Okay. It could be that the cost is very high, but
The cost can be as high as it can get, but
there will
it
be
cannot
always-
be unfeasible.
So you have to solve n problems. What's the complexity of each problem given the task dimension? Okay.
Can you define force tasks for the end effector?
No. If it's in contact. You cannot apply force.
Yeah,
in the
of course.
I say it because some people do it. They talk about forces even when the robot is not in contact. Like virtual forces.
Mm-hmm.
So it's time